Hello, my name is Spencer Whitehead, and I will be presenting our work on separating skills and concepts for novel visual question answering. This is joint work with myself, Hui Wu, Hung Ji, Ruggiero Ferris, and Kate Sayenko. Existing VQA models typically lack compositionality and often entangle concept and context representations and don't truly ground concepts. In this work, we seek to measure and improve compositional generalization. How do we characterize this lack of compositional generalization? Prior work has often defined compositionality in VQA as questions that involve complex chains of elementary operations. This is often not seen in human-written VQA questions. In this work, we look to humans. Humans answer questions by executing the relevant skill based on the concepts in the question. Humans can seamlessly compose skills which provide the question context and concepts. This is the view with which we want to evaluate compositionality in models. This allows us to evaluate under two circumstances. One, novel skill concept composition VQA, where label data for a specific skill concept composition is removed from training, and then we test on novel questions containing these unseen compositions. And second, novel concept VQA, which is a challenging setting where label data for a concept in any skill is removed from training. Then we test on novel questions containing the concept without any labeled data having been seen during training. Now, to discuss our approach for improving skill concept compositional generalization, we first introduce the problem setting. In the standard VQA setting, models are trained with the labeled data using the VQA loss. Models can then answer seen compositions mostly correctly, however they can have difficulties on novel compositions. In our setting, we assume we're given some small amount of unlabeled image question pairs, and using both the labeled and unlabeled data, we want to apply some approach to be able to generalize to novel compositions while also maintaining performance on seen compositions. So how can we learn models that demonstrate more compositionality? Our idea is that models should disentangle these two factors. Therefore, we want to 1. Learn grounded concept representations, and 2. Encode skills in a way that are agnostic to concepts and visual content. We want to do this without requiring annotations or data external to the target task, which means we need to utilize the labeled and unlabeled data we have at hand. Hence, we use a contrastive learning approach where the data is effectively the target for our learning objectives. We had two contrastive objectives to learn these properties: concept grounding and skill matching. Our method uses a backbone multimodal encoder for which we use a transformer that we can apply our objectives to. For each objective, the model is given a target example and a reference set of positive and negative examples. Our first objective is concept grounding, where the model must recover the concept mentioned by pointing to tokens in other questions. We input the target and all examples in the reference set separately into the multimodal encoder to obtain multimodal representations of the question tokens. The objective maximizes the similarity between the masked target concept token and the same concept token in the positive example. To obtain references for this objective, we define positive examples as ones that contain the target concept while negatives do not. We further refine these references to encourage the model to utilize visual information by making the positive examples have distinct textual and visual context from the target, and negative examples have similar textual and visual context to the target. So the negative examples act as distractors. For our skill matching loss, again, we input the examples separately into the multimodal encoder and mean pool the token representations to obtain a single multimodal representation for each question. Our skill matching loss makes the representations of questions with the same skill more similar and is concept agnostic. We utilize contextual similarity of the questions to judge whether or not questions have the same or different skills. The model is then trained jointly with a combination of concept grounding, skill matching, and VQA losses using a multitask learning procedure. First, we experiment on novel skill concept composition VQA. We compare against compositional models, which are neuromodule networks, as well as transformer architectures. We see compositional performance improvements of our method over the base model. The main takeaway is that disentangling skills and concepts can improve compositional generalization. Here are some qualitative examples comparing outputs with and without our losses, where we see noticeable improvements despite not having labeled data for these compositions. As previously mentioned, we also evaluate with a more challenging setting where the models see no labeled VQA data containing a specific concept during training. Our losses consistently improve over the base model in this setting as well. We also explore the performance by asking, are we actually learning grounding? We annotate 320 image question pairs for concept grounding and compute recall at 5 by measuring the similarity between concept tokens and image regions. Quantitative and qualitative results show that our losses can markedly improve concept grounding. Overall, in this work, we introduce a new view and evaluation setting for compositionality in VQA. We present a novel contrastive learning approach for disentangling skills and concepts, and experiments demonstrate the potential value of this kind of disentanglement. Thank you very much, and please feel free to reach out